Hello and welcome to the Computer Vision Festival, hosted by the AI Accelerator Institute, a global community of over 400,000 AI leaders and practitioners, all striving towards one shared goal: inspiring the next generation of machine intelligence. With expert presentations on the festival agenda covering everything from space exploration on Mars to self-supervised learning, you're in for a treat. If you have any questions for our speakers or want to connect with them further, then ask away in the comment sections of the video and hear them answered at the end of each session in our live Q&As. If throughout the day you're loving the content, then be sure to check out the AI membership plans, where you can get access to exclusive content in the form of interviews, reports and articles. Access all areas passes to all past and future events. You can also join our Slack community, which is home to more than 2,500 fellow AI, machine learning and computer vision professionals, and is full of dynamic conversations and contributions. So if you're not already a member, come and join us today. Sign up using the link on the AI Accelerator Institute website. I want to say a massive thank you to all of our sponsors and partners for helping us to bring the festival to your screens today. Our amazing speakers for contributing some awesome content, and to you, our attendees, for joining us today. That's it from us, so go ahead, sit back, relax, and enjoy the festival.
Hello everyone, and welcome back to the second session of day 2 of the Computer Vision Festival. It gives me great pleasure to introduce our next speaker, Dr. Ryan Alamo, who is the lead machine learning scientist at NASA Jet Propulsion Labs. Sorry, I can't talk. And he's here to talk to us about computer vision on Mars. So I'd like to welcome Ryan to the virtual stage.
Yes, thank you so much, Heather, for such a nice introduction. And hi, everyone. I'm live from LA, so Los Angeles, California, and I'm going to quickly share my screen and we can... Oops. So let me know when I can start.
You are all set. I can see your screen. I can see you. We're good to go.
Hi, everyone. My name is Ryan Alamo. I am a machine learning scientist at NASA's Jet Propulsion Laboratory, California Institute of Technology. I'm very excited to be here at the AI Computer Vision Festival to talk to you about some of our incredible work that we have been doing at JPL and computer vision for Mars exploration. This photo that you see is, in my opinion, one of the best selfie photos I've ever taken, and it shows the Curiosity rover on Mars, and it took a picture of itself, right? And the next giant leap that we're going to have is for sure human Mars exploration. And when I was in high school, I read an article about human Mars exploration, and that excited me a lot. And when I came and became a researcher at NASA JPL, I found that this is one of the most exciting, but also most complex engineering problems that we're going to solve in the next decade. And there are lots of complexities. However, when we want to explore, the red planet, the next giant leap is going to be human AI teaming. So we're going to be surrounded by a number of robots. It can be the flying ones. It can be, landers, rovers, and they're going to help us to achieve this big vision. Over the past several, decades, we have had an evolution in terms of how we explore other planets. In 70s, 80s, 90s, and 20s, we observed that we first had the flybys. There was a satellite that just crossed different planets, such as the Voyager 1. Then we had orbiters and landers, and now we have the helicopter on Mars. That here is one of the latest photos of the Ingenuity Mars helicopter. That you're going to see the Perseverance rover on the left-hand side. This is the small rover. However, in practice, you see that the rover is way bigger than the helicopter. And the size of this rover is as big as an SUV. And now it's flying on Mars, it's driving on Mars. And one of the challenges that we observe here, and many of you also ask, is what types of autonomy we have. And one of the surprising things that when I first heard about that was this rover, the top speed for the Perseverance is 5 centimeters per hour. The next rover that we're going to have, which is going to be the collaboration with the ESA, the European Space Agencies, is going to take the samples that the Perseverance took from Mars and put it in different tubes. It's going to go and collect them from different parts of the Mars and then put them together and put them in one rocket and send it back to Earth. And this new rover is going to have a top speed of 1 kilometer per sol, which is significantly faster than the existing rovers that we have. So that brings lots of complexities and lots of machine learning and computer vision into the table that we need to solve. One of the problems that there are a number of challenges. One of the main challenges that we have in Mars exploration is the communication challenge. As you know, Mars is very far from us, and there is an urgent need to have more advanced onboard processing or the edge computing on the rovers to make online decision-making capabilities. When the data is sent back to the Earth, we typically observe that there is about 60 megabyte data per sol is Martian day, is going to be transferred to the Earth. That's due to the physical challenges that we have. The Deep Space Network is a center that NASA has in different parts of the world. One is Australia, one in California, and one in Madrid that takes this data from Mars. But daily, we're going to have much more amount of data that we collect, maybe in terms of the gigabytes, or maybe later it's going to be a terabyte of data is going to be gathered, and it's going to take a while to send those back. And these new the new autonomy capabilities is going to help us to tackle both the self-driving capabilities, the technological advancement perspective of the rovers, as well as maximizing the science work. The other main challenge that we have, which some of you also asked about this, is hardware limitation. The onboard processing that is available on the rover is called RAD750, which is equivalent to an iMac from 1980, 1998. And that's quite, less powerful than the existing cell phone cell phone processor that you have in your pocket. We are working on different projects to overcome this issue. For example, one of the active projects that we have, which is with a joint project between NASA and Air Force, is called High Performance Spacecraft Computing, or HSPC. That is rad hard. Rad hard means that when you go to space, it's going to be in the hard radiation scenario, you're not going to have any problem, and you can still work, and your processes can work reliably. And the HSPC chip integrates into it has a couple of components. One of them is the the quad Cortex A53 ARM CPUs, and the other part, the real-time processing subsystem, and overall, it's going to be a suitable processor to work in harsh environments such as Mars. The other trend that we observe is using commercially off-the-shelf hardware. This year, we observed that Ingenuity flew with Snapdragon. And Snapdragon is available in your cell phone. And this Snapdragon 855 has the capability to run deep neural network in real time with the support of GPUs and digital signal processing. So it's going to have a more capability in terms of what we can do with the computer vision algorithms and onboard processing units that we're going to have on the red planet. So this leveraging the existing commercially off-the-shelf sensors is opening a new era for space exploration. On the left-hand side, you see the Mars helicopter that runs on Snapdragon. On the right-hand side, you see a CubeSat that's called Marco that in 2020, it passed the Mars, and it flew with the InSight lander. And these spacecraft are much cheaper to build, and they usually leverage the hardware that is available to you. So this creates a new capability for us for testing high-risk, high-reward projects. One of the projects that I have worked with my colleagues at ASU and JPL was building computer vision capabilities to build in-orbit assembly. So in this work, we have developed a molecular-based pose estimation algorithm based on the convolutional neural network that takes an image, right, first in the simulation environment and then in the real-world setup, and predicts the pose, which is the relative distance and orientation of a known object. And after that, you can grasp it and put them next to each other and build a much larger structure in the orbit. So you can take different parts, small parts, and then you assemble them in the orbit to create a larger structure. When we talk about the Mars rover, we observe that we have been doing this autonomous driving for decades. So my colleagues at Jet Propulsion Laboratory, Dr. Tupe, Dr. Ono, have worked on a number of different autonomous, navigation platforms, such as the AutoNav and Enhanced AutoNav, that enables us to drive smoothly on Mars and create a train online, and you can observe where you are driving and where you are heading to. However, we observe a challenge. One of my favorite rovers, Opportunity, got stuck in the sand, right? So we were thinking that based on the images that we took from Mars, the area is going to be safe, but unfortunately there were a hole and the rover got stuck. Spirit also had the same problem. That's why we observed that computer vision and semantic understanding of the terrain is a critical element in Mars exploration and for the rovers. So in this project, you see that one of the robots that we have at JPL called Athena is navigating into the Mars yard that we have at JPL. It's a small part of the Mars, and it navigates, into different areas, and it builds a semantic information around itself, where it's the safe area and where it's not a safe area. Also, there is another project called Mars that using citizen scientists, we were able to label about 300,000 images that shows that what type of terrain you have. Is it the soil? Is it bedrock? Is it sand? And after that, validation has been processed with the rover driven like drivers and also geologists, and using a pre-trained model as well as these data sets that all people around the world helped us to create in a project called Mars AI. We were able to predict different trains, and here is the result that is summarized in the papers that Dr. Ono and his colleagues wrote about in this area. Once you have this information about the train, you want to know that very safe. consider this Mars sample return, which is not nuclear based. It is the solar panel. It's relying on the solar panel in order to go from one location to the other location. It is not usually the best idea to take the minimum distant path, because that may end up in a non-safe and you may not get to the area that you want. Maybe it's better to take another path that is safer, and then you wait for a day or some time to recharge, and then move again and reach your destination. So this in this work, you can also predict, how much energy you're going to have, and you can consider that in your optimization problem for the path planning. And given the information that you have from the semantic information, you can in your cost function, you can quantify very safe and very not safe, and get your destination in different waypoints that you have. So in the next part of my talk, I want to talk about scientists and how computer vision helps the scientists. This is one of the photos that are taken with Mars Reconnaissance Orbiter. It's one of the orbiters around the Mars that shows these dunes in one part of the Mars. And it's quite interesting and quite lovely. We can gather the information that we take from these satellites around the Mars. One of them is MRO, and classify them into different types. And this enables us to do more autonomous, classification and understanding about the images that we collect. Also, this is another data set that a colleague of mine, Dr. Curie Wagstaff, have worked with her colleagues that shows the engineering-based data set. So this is the MSL, Mars Science Laboratory, or the Curiosity rover. It took a couple of engineering images, and you classify them into different classes, and you try to predict what class it is. And the other one is about the orbiters, and you want to understand what type of terrain or object you're observing from the Martian orbit. The big vision for us is, as we have these spacecraft that are going to Mars or other planets, and we have a limited number of people, like scientists around the world, right? It's going to take many. In the past, it took a couple of years to found that we have done a revolutionary. We found a revolutionary image, or we found one of the best scientific facts on Mars, because we gather lots of images. There is no help from the or there is no help or annotation in terms of, okay, we need to pay more attention to this area or this image rather than the other part. And then in the next generation of the rovers, we have more autonomy. So one of them is Dr. Estlin have worked in a number of novelty detection algorithms that it finds what areas are more important, and we can have more likelihood of having great discoveries, and the other parts are with my other colleagues. But in the end, what we are heading to is how we can have a science drive-by. Imagine the Mars sample return. So the objective is to collect these different objects, and meanwhile, when it's driving, you can find some interesting images from the Mars, and it can send those back to the Earth. In that regard, we have another project that is called Scotty, that geologists are captioning different images that we take from Mars. And this is going to be the image captioning architecture, and an attention-based model is going to help us to describe the captions in a sentences in a form of like English sentences after we caption them. Then it is possible to interact with a web app that you can search for different type of trends or different scientific facts, and the similarity measurement is gonna give you some of the most interesting scientific facts that is there. Overall, we can have different elements for computer vision. One part is going to be the rover. So the rover can take an image, and then it is it sends the data to the stereo for finding the distances on a train, reconstruction, globalization, localization. Also, it can send it to the convolutional neural network that in this situation, when we had it in the test, so it is in a we can calculate in a deterministic manner and use backpropagation techniques with stochastic gradient descent and adaptive learning to find what the encoder part does and have an encoder decoder network that is using convolutional neural network to extract different features or the elements that you have in the form of a vector. And after that, we can use a decoder to give it to the the planning team and find about different elements and segmentations. And also you can give that information to the novelty detection like novelty detection framework, and after that we can use an LSTM, long short-term memory network, that produces a caption for us, and it generates the words in a context vector. And the other part is going to be, let's say, the convolutional neural network, that it can in an example we use VGG19 with a pre-trained model on ImageNet that is using the feature extractors. And all of these can be summarized in a form of a database. And when the scientists look for specific scientific facts or a specific thing, it gets the data from like Elasticsearch, possibly somewhere closer to Mars than us, because of that communication delay, and we get the interesting science work from this area. So this is a number of great works have been done in this area and was led by different people, and these are the summary of the works. AI for Mars, and also the Mars project, that I highly encourage you to read those papers, and they have done with my based on my colleagues and other people's work. The other work that I've been doing is, when we see these large data sets, we can leverage different sensors in order to visualize them. For example, this is the HoloLens that you can use. It's one of the great tools that you can visualize the 3D data, which is not a common data, at least it was not common in the past. So this scientist, when you get the data, there are lots of holes if you use these panoramic images or different parts. So you want to have a high resolution images and minimize also the scientific facts that you have. You don't want to augment the data. So how we can use 3D deep learning in order to reconstruct unstructured areas. And in summary, what I want to conclude here is computer vision plays a critical role in space exploration, especially exploring Mars. There is a limitation in terms of the onboard autonomy for the processors, and that's due to the rad hard constraint that we have. We need to be work in the harsh environment that radiation is there. In the next missions, we're going to have more autonomy in terms of the science work, as well as driving. We want to drive like a faster to collect some of the objects. The computer vision helps us in technology perspective, as well as in increasing the science discoveries. And I know we have a limited time, and with that, I'm going to answer some of the questions that you have. And just as a final note is, I've heard that we have the most number of attendees in this talk. So it means that we have a great enthusiasts. This is a very interesting topic that people want to work on, and they want to be part of it. And if you are interested to work in some of these revolutionary works, please email me, send your resume, and we can see how we can collaborate. This is an international work, especially if we want to explore, human Mars exploration mission. That's going to be a project that all of the citizens around the world needs to work on that, and for sure we are limited in terms of how much we can do. And please feel free to contact me and ask any questions that you have. And with that, I would be happy to answer your questions.
Okay, thank you so much, Ryan. Yeah, what a fascinating presentation. No wonder it gained the most traction with our audience. Ryan wasn't lying there. You did actually get the most sign-ups out of all the talks throughout the 3 days. So yeah, let's get in some really cool questions for Ryan while we have him. So we'll start with a question from Mohammed. Ryan, so let's just get rid of your presentation unless you still want it up.
Yes.
Cool. So do you take additional procedures to prepare the model for new distributions? How do you acquire a relevant data set when you have limited images from Mars, in brackets, driver's view? So
that's an excellent question. Is it possible to read out again?
So do you know what? I'm going to send it to you privately, Ryan.
Okay.
So you can take a moment just to have a little read through it.
That's an excellent question, right? So it's referring to the transfer learning and how we can find, or meta learning as well, how we can find relevant data sets in our in this domain that we are working on, and increase our image size or our training size for machine learning. So one of the things that is challenging for sure is how we can generate metadata or other data sets that are close to us, close to the Martian environment, and have at least a prior knowledge or pre-train. That is one of the challenges. We don't know many things, how the Mars is going to look like. But we observe that some areas on the Earth is similar to Mars. So we can take and gather information in some areas such as the Mars Yard or other areas that look like Mars, and pre-train our network and use those data sets. But for sure, that's the biggest challenge. And as Dr. Chin mentioned that, Steve, yesterday, NASA is more in the knowledge business rather than the data business. So yeah, that's an excellent question.
Okay, yeah, thanks for your answer there, Ryan, and thanks, Mohammed, for pitching in with a question. Next up, we have a question from Peter Horling. So, hi, thanks for an amazing presentation. Can you elaborate a bit around the safe, not so safe declaration, purely based on camera data? And if so, how was the cost function designed? Once again, Ryan, I'll send it to you privately just so you can have another read.
Again, that's another excellent question in terms of the safe and unsafe areas and how we can form it in the form of an optimization problem, right? So when you, in the form of an optimization problem, usually you can consider those as let's say, if you understand somewhere is not safe, you can consider as a collision and add that as a penalty or as a constraint in your optimization and trajectory planning platform. In terms of what is safe and what is not safe, we just go back and see the example that I showed, right, in the opportunity case. So there were a hole, right, and it was covered by sand, and we didn't, by the image from the Earth, we didn't know that there is a hole, and sand is covering those. Usually what we observe is sand is kind of risky to drive on the top of it, and this is this is one of the things that we can consider, that an area that we see is rocky, let's say, and there's sand over there, so we need to wait. Maybe there is like a wind comes and cleans that area, and we can make sure that we have a path to go, or we just avoid that area, because in the problems that you have on Earth, if you get stuck somewhere, you can go out and take the, you can get some help from others and come out from the hole. But on Mars, that's not a possibility, right? And these are billion-dollar projects, so you don't want to risk it, and you are not in rush as well. So that's you can drive slowly, 5 centimeters per hour, but remain safe.
Okay, great. Yeah, great answer, Ryan. So we've got about 5-7 minutes left, so we'll try and get through the rest of the questions. But I'm sure Ryan would be happy to take up any questions that you have via LinkedIn after this session. So a bit more of a generalized question here from Tonislav. What computer vision is used for landing? Interesting.
Yeah, that's an interesting question for sure. So when we talk about landing, there are different perspectives in terms of computer vision. One of them, radar sensors that is going to measure the depth, LiDAR sensor as well. So one area that you want to explore is how close you are compared to the surface. The other one is, and then creating the digital elevation map. The other one is finding out where is safe and doing image classification and image, and finding an area that is safe enough. So in that regard, yeah, there are different computer vision algorithms from the traditional perspective and neural network. But one thing that you want to consider is the execution time on those limited processors. So you can tailor it to specific application and yeah. So this is a mix of the traditional and possibly neural network based.
Okay, great. Thank you so much, Ryan. And there's your answer, Tonislav. So Gisel, thanks once again for posting a question. So can GANs be used for generating the Mars data?
That's a work many people have tried, and I encourage the gentleman or the lady that if they have been successful in doing that, please contact me. Right, this is an interesting area, and one of the things that is important for scientists is how, when we get the data, we want to make sure this is a scientific fact, right? That's why they are hesitant to work with any machine learning, algorithm. At least that was the past. They want to get as many raw data as they can, and they know their job, and they can do the science work. This perspective is changing as we have more data, but if you use GANs, suddenly you may have something that is irrelevant. And GANs usually require huge amount of data that we don't have that luxury.
Okay, cool. Thank you. So a couple of generalized questions there from Mahendra, but perhaps that's something you should ask Ryan over LinkedIn, just about the opportunity to work with NASA JPL. And then moving on to Gunter's question. Hey, Gunter, and thanks for your presentation yesterday. That was awesome. So Gunter is asking, is there a GPS-like system on Mars which may support navigation?
Well, there are a number of orbiters around the Mars, right? More than 6 orbiters around the Mars that are in communication with the rovers. And the GPS in a form of what we have on Earth, not yet. But that's also in our, let's say, long-term vision that we have. When we have enough rovers or enough different elements, so we can create some sort of like a GPS type.
Okay,
cool. But we are in communication with the constantly with the orbiters, and those send the data back to the Earth, to the DSN, deep space networks, and then to us.
Cool. Thanks, Ryan. So we're just running out of time now, so we can squeeze in a few more questions. So sorry to everyone if I haven't, or sorry to anyone if I haven't got around to your questions, but we'll take this one here from Prashan. So given that AI-based models are rapidly evolving, is it possible to upgrade the AI model to a better version, perhaps a better model trained with more data, in a rover that is currently on Mars functioning with an older model?
Well, you don't want to risk the rover, right? So one thing that is important is you don't want to have a new scientific or new algorithms running on the rover. You want to have the safest possible algorithms out there. So what we can do and what we are doing is evaluating these algorithms on Mars yard or areas that are close to Mars, and then we can do it on Earth, but we cannot risk the rover. Also, you have limitation in terms of the hardware.
Cool, thank you very much. So Amartya, has there been situations where the model couldn't recognize what it was seeing? If so, what happens then? Because to identify it again, it would require more such samples. So do you augment?
That's a great question. And there are some dates, like let's say for the terrain classification, there's some data augmentations available. Like in one of the work we used, I guess the paper in my college used Deep Lab v3, and we did pre-trained models from available data sets, and the citizen scientists, the 300,000 images they use. So we use the it is the data augmentation. You can use the data augmentation, but in the real rover, you don't want to risk it. So on Earth, you can do whatever you want, but not in rover.
Cool. So we'll do two more questions. One from Wendy. Hey, Wendy, are there particular models that work better with the current hardware than others? Was curious if that was an issue. Came in as you was discussing the limited hardware. So the question is, are there particular models that work better with the current hardware than others?
So FPGA is very common for in space. Right? There are custom design hardware, and for sure you need to have a custom software at the same time. And answering to the question, we need to design the algorithms for the FPGA and for the hardware. And you cannot use one of the codes from the GitHub and then try to run it on a new hardware. So it needs to be tailored to a specific application. And one of my colleagues mentioned that AI cannot be purchased. It needs to be built and customized for your application. And this is exactly the example that we have in NASA. So we cannot buy it. We need to create it, but we can use the prior knowledge that is out there because fundamentals are the same.
Okay, cool. So hopefully that answers your question, Wendy. And Aid, or Addy, do you see any sensor fusion techniques in deriving visual odometry on Mars? What sensor modality was most important?
For sure, yes. The fusion sensor is helpful, but this is again a little bit more involved than I can explain it in a short. But the sensor fusion, such as the self-driving cars, right? So you have a system that wants to drive, so you have different sensors. But again, you don't want to endanger the rover. You want to be safe. That's why you take the image, you wait for a day to get back, from the scientist that area is safe or not, and then you can drive over there, rather than instantly making decisions and going to an area that is you're uncertain about.
Cool. All right then. So that is all we've got time for, unfortunately. There is loads more questions still coming in on the Q&A and on this chat. Deeply sorry that we couldn't get around to them. So just a huge thank you to yourself, Ryan. It was a very, very fascinating presentation. As you can see, the audience loved it. And to all those in the audience, I'm sure Ryan would be more than happy to carry on this discussion. Just send him a message on LinkedIn. Like I've said before, all of our speakers' LinkedIn and company websites are on the main festival website, so you can get his details that way. But yeah, big thank you to the audience for tuning in. I'm going to send the next link to the next session in the chat box now. But yeah, huge thank you to you, Ryan.
Thank you so much. You can also email me, and wonderful, and have a great day. I'm looking forward to seeing revolutionary works from the audiences.
Thank you so much.
And thank you so much, Jordan, for all of these. You know, Jordan and Heather, you have done a wonderful job. I know it's really hard to do organize all of these things, and thank you so much for all of that.
It's been a pleasure. It's been a pleasure. Thanks, Ryan. Take care.
Thank you. Bye-bye.
Bye-bye.